Now we're going to continue with the consideration of the axon. And there were two questions left unresolved by the last lecture. So the general question is, what's so special about an axon? We've already considered how action potentials permit the transmission of electrical signals along the membrane of the axon. Next, we're going to look at how those action potentials propagate along the axon in one direction and how they do so quickly. All right, so our question is how? How is it possible that axons are capable of these feats? And the answer to that question is going to come from a consideration of the membrane properties of the axon. So how do they move in one direction? Let's perform a virtual experiment where we have a recording electrode close to the axon terminal. That's the most sort of distal part of the axon. And we're going to see what appears at that site of the recording electrode. That would be right there. If we manipulate the system by stimulating it. So for that, we're going to insert a stimulating electrode at a more proximal position. And what's a stimulating electrode? Well, that allows us to manipulate the membrane potential. And in particular, if we allow for a flow of sodium ions at that site, then we can experimentally create a depolarization. We can trigger an action potential. So just like if you had a voltage-gated sodium channel at that site, you're going to have sodium flux that will move down its chemical concentration gradient and thereby create a controlled depolarization. Okay, so now what we can do is manipulate the system, manipulate that little patch of the membrane, and monitor at the recording electrode what happens. So that's what we have in this plot here. So let's, for example, create a depolarization that's much like an action potential at the stimulating electrode, like that. And then we're going to step through how that looks at the recording electrode. So initially, we start off at the resting membrane potential, and we're going to define time 0 as when the depolarization begins. Now, what we'll see, which is we're going to create an action potential here. So all of the steps of an action potential, since it's an all or none phenomenon, are going to look exactly like we've talked about in the last lecture. So we have the depolarization that's driven by the depolarization just upstream of it. Okay, so we have the stimulus that we're creating here. That's going to trigger an action potential that's going to propagate. So what we're seeing at the recording electrode is the depolarization created by sodium in that region, not what's generated at the site of the stimulating electrode. The stimulating electrode serves to just start an action potential. So here we have that depolarization at the recording electrode site. If it reaches threshold, minus 55 millivolts, then boom, we get our action potential. And it just plays out the same way every time. Now, let's do an experiment where we give it just enough of a stimulus to create a small depolarization. And that small depolarization is only barely sufficient to create an action potential that we're going to see at the recording electrode. And then we're going to do that a second time. So while the membrane is hyperpolarized, we generated a second, just barely sufficient depolarization at the stimulating electrode. And what we find, this is the result here, we see no change. It's just the same action potential that was driven to threshold initially. The second stimulating action potential, or I should say stimulating depolarization, does not successfully generate an action potential. What if instead of a sort of barely sufficient depolarization in that second stimulus, what if we crank it up and stimulate the membrane with a much more substantial depolarization? If we perform that experiment, then we get the result that looks like this. Boom, we get a second action potential. All right, so it is possible to get two back-to-back action potentials, but the stimulus that was just sufficient to create the first action potential is insufficient to trigger the second one. Instead, the second one has to be stronger. Okay, now if it's strong enough, we end up getting an identical action potential. Again, action potentials are all or none. Okay, so if we're getting an action potential, it plays out the same way, or the none would be we get no action potential. Now, this period of time between 2 and 4 milliseconds from the onset of the first action potential, this period of time is known as the relative refractory period. And the relative refractory period has some important characteristics. So the first of all, you need that strong depolarization in order to create an action potential. There are two barriers to generating an action potential. The first is the threshold changes, I should say the threshold is different during the relative refractory period. So instead of the negative 55 millivolts that we needed to initiate the first action potential, here we see that the action potential is the threshold is greater. That threshold changes over time, and by the time we reach 4 milliseconds, this is a little bit misleading because once you start the second action potential, then everything changes. But this dotted line shows us what we would have to exceed in order to create that second action potential. So this relative refractory period corresponds to it's the relative refractory period relative to the first action potential. So this 2 to 4 millisecond period of time is relative to that time 0. Now, this second action potential would have its own relative refractory period going from 4 to 6 milliseconds, or given our convention here, we would reset time as 0 being when we initiate the second action potential. Okay, so the relative refractory period is relative to that first action potential. And relative to that first action potential, we have a greater threshold. And that's one reason why we have to have this stronger second stimulus in order to create the second action potential. The other problem is right here. The membrane starts instead at the resting membrane potential of minus 70 millivolts. We're below that here. And so we have to drive the membrane up to that level and then drive it further to reach that higher threshold. So the fact that the membrane is hyperpolarized is another hurdle that has to be cleared in order to create that second action potential. Okay, what if we give the membrane a really strong depolarization, just like we see here, the second depolarization, but it's within the first 2 milliseconds of an action potential? That's what we see here. What do we get? We just get one action potential. And that's because this period of time between 0 and 2 milliseconds is known as the absolute refractory period. And it's impossible to get a second action potential from a stimulus that occurs, a second stimulus that occurs in those first 2 milliseconds during the absolute refractory period. All right, so we have absolute and relative refractory periods. These are interesting properties. We're going to see that they're really important for understanding how the axon functions in a moment. But first, let's consider the mechanism. What is it that causes these refractory periods? And so let's step through time. So first, we're going to start early in the absolute refractory period. And at this time, the membrane is ready to go. And so when we issue that first, just barely sufficient stimulus, we have a whole bunch of voltage-gated sodium channels that, once the depolarization gets going, have opened up their activation gates. So this illustration shows us our population, and this would actually correspond to a point in time while the depolarization is occurring, because what we see here is all of these voltage gated sodium channels that are opened up. Okay, these have already been activated, and that activation is driving the depolarization. So early on, you would expect some subset with their activation gates closed. They haven't yet been activated. And then by the time you reach this peak depolarization, then the vast majority would be in this state that we see here. Whereas the absolute refractory period, since it extends over 2 milliseconds, it also includes the repolarization that occurs here. And so if we look late in the absolute refractory period, then there's going to be an increasing number of channels that look like this. That is, their inactivation gates have been activated and they have shut off the membrane's permeability to sodium. Now, some haven't. And as you march through time, there's going to be more and more that have the inactivation gates closed, thereby driving a reduction in sodium permeability by the membrane. Now, if we march through time and we consider the relative refractory period, now all throughout the relative refractory period, there's going to be some proportion of channels that are ready to be reactivated. And they look like this. The inactivation gate, the sequence from this state would be that the activation gate swings closed. And this isn't actually a door, of course. It's just a domain of a transmembrane protein that resets to its initial configuration, which is blocking sodium permeability. And then after the activation gate closes, then you have the inactivation gate opening, okay? Because this is the initial state. This is where we started here with the membrane at rest. This corresponds to the channel being ready to be activated. But early in the relative refractory period, lots of the channels still remain in this inactive state. The inactivation gate is not permitting sodium flux, and it can't be reactivated by a change or a depolarization in the membrane potential. This explains why the threshold is higher early in the relative refractory period, because you just had a small proportion of voltage-gated sodium channels that are ready to be depolarized again. And as you move through time, you have more and more voltage-gated sodium channels in this state where they're reset and ready to be activated. Okay, so if we look late in the relative refractory period, what we find is more and more voltage-gated sodium channels in that state, like this, okay? And if they've been reactivated again, you might see some in this state, okay? This is going to drive depolarization, just like the initial action potential, but most are going to be in this state here where they're ready to be activated. Okay, now the refractory period, even though we're only considering one little patch of the membrane, it relates to the propagation of action potentials along the axon. So let's zoom in on a patch of the axon here to see how that plays out. All right, imagine up top we have a depolarization. So we have voltage-gated sodium channels being activated, allowing for an influx of sodium. That's going to create a depolarization in the region, not just where the voltage-gated sodium channels are, but because the sodium is going to move down its concentration gradient in not any particular direction, but as a population, the sodium is going to just start to infiltrate the regions of the axon that have not been depolarized. And what this is going to do is have an effect on the membrane potential in all regions. Okay, so right here we have a patch of voltage-gated sodium channels at the resting membrane potential ready to be activated. So as the sodium diffuses into this region, it drives another depolarization and the action potential moves. Okay, now here's where the refractory period matters. This first region where we had the action potential transitions from the depolarization of the action potential into first its absolute and then its relative refractory period. So what that means is that in this new site here, as the sodium infiltrates into the axon, it cannot reactivate that little patch of membrane that was just activated. So here we have the sodium moving into the axon, and here it can activate the membrane, but not here. So the refractory period instills the membrane with a memory. It's very short-term memory, but the memory essentially is making it so that the membrane remembers that it just went through a depolarization as part of the action potential, and it's now going to be insensitive to another depolarization. So we don't have a reactivation of the action potential in that region. Instead, we can have a depolarization down here. And that's exactly what happens. Provided we exceed the threshold, we're going to get that depolarization. And it just marches on and on towards the axon terminal down here in the distal region of the membrane, leaving in its wake the absolute refractory periods that make the membrane insensitive to another depolarization. So here's a question. Now that, what this illustrates is how you get unidirectional action potentials. It's because of the absolute and relative refractory periods that you cannot reactivate the membrane, and as a consequence, you only get action potentials going in one direction. So let's perform a thought experiment. Instead of the typical case where the action potential is generated close to the cell body and begins the propagation to the distal reaches of the axon, let's experimentally introduce an action potential right in the middle of the axon. And let's just consider what happens there. So the question would be, in what direction do you get the propagation of an action potential? Let's see what happens. We're introducing sodium. That causes a depolarization in that region. The sodium is going to diffuse in all directions. Sodium itself has no directionality. It's just going to move down its concentration gradient as a population. Now, in both adjacent regions of the axon, we have a low concentration of sodium. So the sodium will infiltrate both regions, and the membrane in both of these regions is ready to be depolarized. The voltage-gated sodium channels right here and right here are in their resting state. Their activation gates are closed. The activation gates are closed. The inactivation gates are open. So what that means is that those two patches of membrane can now be depolarized. And the middle region, which began this stimulus, moves into its absolute refractory period in blue and cannot be reactivated. And so the sodium that rushes in here and here is not going to reactivate this patch, but it can activate the other regions that haven't yet been activated, like that. And then those two patches here and here transition into their refractory period, making them insensitive to the sodium that flows in where you have the leading edge of the action potential. Okay, so in this experiment, we started the action potential in the middle of the axon, and we found that it propagates both towards the soma, that is upwards in our drawing here, and towards the terminal, downwards. So this answers the question of what's so special about the ability to generate action potentials in one direction. It's because of the refractory periods that cause an action potential to move away from where that action potential began. Now let's consider the speed of the propagation of action potentials, because there are a wide variety of axons, and some, like the axons that reach from your spinal cord to the muscles in your toes, that's a really long cell. That's one cell that activates the muscles in your toes, and it has its cell body in your spinal cord. Now that's a situation where if you're, say, stepping on a tack, you want the muscles in your feet to respond, to recoil, to avoid impaling your foot any further upon that tack. And so the activation of those muscles quickly really, really matters. And so what you find is the axons for cells that are really long have modifications to enhance their speed relative to really short interneurons. Those are neurons that are connected to other neurons. Really short neurons don't have these features. All right, so what are those features that make axons propagate signals fast? Well, here what we have is a cross-section through one little bit of our axon here. And of course, we have that high concentration of sodium outside the cell. Now, as this action potential propagates towards the terminal, we see that the membrane in our cross-section is activated. The voltage-gated sodium channels allow for sodium to move into the interior of the cell through facilitated diffusion, and then eventually that sodium, or those channels, become deactivated. Okay, so what we just saw, and let me play that again. After this influx of sodium, there's some amount of sodium that is going to be either pumped out of the cell or will just diffuse through the cell membrane. And so you can think of this as a form of inefficiency in the transmission of an action potential. Membranes leak some of those sodium ions, which is going to slow the action potential transmission, because if there are fewer ions in the interior of the cell, that means there's going to be less propagation of the depolarization in the region of that axon. Okay, so this leakiness is a problem. And so there are two measures that can be taken to combat the leakiness that occurs here. One is just making the axon larger in cross-section. If it has a larger diameter, then the sodium ions have more space within the interior of the cell to diffuse and not make their way back out of the cell through the cell membrane. So for example, here we have a much larger axon. The depolarization allows an influx of sodium, and a lot of those ions are going to remain in the interior. A smaller proportion are going to leak out. The other strategy to avoid losing sodium ions in the interior is essentially to insulate the axon. And that's done by another cell type. Here we have one of those insulating cells. We have this green color. Now, when the sodium diffuses into the interior of the cell, it just bounces around and is prohibited from leaking out of the cell. Now, these insulating cells are called Schwann cells, and we see one in green. There we have a whole series of them. And this insulation is known as myelination. Okay, so Schwann cells are the cell type. Schwann cells provide myelination of an axon. And it is typical in a myelinated axon to have a whole series of Schwann cells with little gaps that separate them. Now, how does a Schwann cell generate insulation? Well, you can think of it as being very similar to any cell in that the cell membrane slows chemical diffusion. And the way Schwann cells are kind of special is that it takes that insulating property of any cell membrane and repeats it over and over again. And the way that occurs is that over the course of development, the Schwann cell will wrap around and around and around the axon. And so if we take a cross section through a Schwann cell and an axon, that's what we see here. So here's the cytoplasm of the axon, and all of these little rings, it almost looks like rings in a tree trunk. Those are the cell membrane for a single Schwann cell. So I think this is the nucleus for that Schwann cell, and the cell membrane is just wrapped around and around and around the axon. It's just using the insulating properties of the cell membrane, and by wrapping it over and over again, it creates a thick insulating barrier. So myelin provides electrical insulation for an axon. A myelinated axon is one that has these cells that provide insulation. Now you might ask, how is it possible to propagate an action potential when your axon is completely insulated? Inside of the Schwann cells, there are no voltage-gated sodium or potassium channels. So you don't have the machinery to create an action potential in those spots. Okay, that's potentially a problem. It's a problem that is resolved by these little gaps in between the Schwann cells. Okay. These gaps are known as the node of Ranvier. And those little regions are packed with the voltage-gated channels that create action potentials. So let's see how this works in practice. We're going to again introduce a stimulating electrode, and we're going to monitor what happens to membrane potential with recording electrodes. So here we've got the stimulating electrode real close to the cell body. And then we're going to stick one recording electrode at the first node of Ranvier, and then we're going to instrument the region within a Schwann cell right there in green. And then we're going to take a look at the next node of Ranvier in this darker red color right here. Okay, so what does the membrane potential look like at the first node of Ranvier? It's an action potential, okay, just like you might expect. It managed this, so we created the depolarization, effectively creating an artificial action potential. That action potential somehow survived propagating through the first Schwann cell and appeared at the first node of Ranvier. Okay, we've got an action potential. That's great. What happens within the Schwann cell? Well, we do get a depolarization, but note something here. It's not as strong as the action potential. That means it is not an action potential. Action potentials look the same way all the time. They're all or none. This is not all, okay? It's not none either. And so we have a situation, because we're sort of in a region that's operating by different rules, we don't have any voltage-gated channels, we actually have something different between all or none. We have a depolarization in that region that is being driven by the voltage-gated channels at the node of Ranvier. Okay, just imagine a little flood of sodium ions into the interior of the cell right at that site. And that is what we see reflected in that first green electrode there. Then when we look at the next electrode further down the axon, we again see a depolarization with a slight delay in time. This delay in time reflects how long it takes for the chemical diffusion of the sodium ions to make it to the site of that electrode. And this system is not perfectly efficient. We don't have all of the sodium moving in the same direction. There's some leakiness still, despite the presence of the Schwann cells. And so we get a degradation of the depolarization with distance from the node of Ranvier. But as long as there are enough sodium ions to drive a depolarization at the next node of Ranvier that exceeds threshold, minus 55 millivolts, provided that that occurs, then we're going to create another action potential at that next node of Ranvier. And that's exactly what we observe in our little virtual experiment. Okay, so we've got two action potentials. In between, we have something that is less than an action potential. And the term that we use for depolarizations that are below the magnitude of an action potential, that's known as a graded potential. All right, so later on when we talk about the dendrites, dendrites only deal with graded potentials because they have no voltage-gated channels. And what we see here is because there's no voltage-gated channels within the Schwann cells, within the myelination, then we also have graded potentials. And graded potentials decrease with distance because they don't get that sort of boost in depolarization that's generated by the voltage-gated sodium channels. Now, the advantage here and the value of having the Schwann cells is that they're allowing for a more efficient propagation of the depolarization within the Schwann cells due to the insulating properties of those cells. And so essentially the action potential is leapfrogging to nodes of Rome VA, skipping over any depolarization, or I should say any action potential that would occur within the Schwann cells. And that serves to really speed up the propagation of the action potential. All right, so the way that the speed, the axons generate very high speed is through two potential mechanisms. Okay, we have this fast propagation that is either facilitated by a large diameter or myelination, or both. And in fact, those really long axons between your toes and your spinal cord are both large in diameter and myelinated, which both serve to speed the propagation of action potentials dramatically.